Welcome everybody to the Fractional Calculus Seminar Series. Today we have Professor Diethelm, who is a professor of mathematics and applied computer science at the Technical University of Applied Sciences, Wurzburg-Schweinfurt, Germany, where he leads the scientific computing laboratory. He holds a diploma in mathematics from TU Brunswick and a PhD in computer science from the University of Heidelberg. His main research interests are approximation theory and its application, analytical and numerical aspects of fractional calculus, especially fractional ordinary differential equations and high performance computing. We are very happy to have you here, Professor. You may please begin your talk.
Yeah, thank you very much, Pavan, for the introduction and for giving me the opportunity to present some of my recent results here. So welcome, everybody. Good afternoon. And I'm going to talk here today about some stability problems for systems of fractional differential equations. And in particular, I'd like to highlight some connections that exist between this question and the theory of so-called nonlinear eigenvalue problems. So this is a concept deeply rooted in linear algebra. Even though it's called nonlinear eigenvalue problems, it belongs to linear algebra. Good. So what can we say here? First of all, let me give you a brief outline of the talk. So first of all, I'm going to say a little bit about incommensurate fractional differential equation systems. What is that, and what is the difference between this and classical other kinds of systems? Then I will talk about the stability of such systems, in particular the asymptotic stability. And to this end, I will very much concentrate initially on linear differential equation systems. This is really the key to the whole thing, and later on in the next section we will then talk a little bit about how all of this can be extended to nonlinear differential equation systems. And finally, I want to mention a couple of open questions, and all of this is based on joint work that I've done with my PhD student Safura Hashemi-Sharaki. Okay, so let's begin with incommensurate fractional differential equation systems. So we're talking about ordinary differential equations, first of all. I won't say anything about partial differential equations here. So this is the kind of system that we have. We have a d-dimensional system of differential equations. Each equation is a fractional differential equation with a Caputo type differential operator of order alpha k. So the k here is the index of the equation, and this equation relates the k's component of the solution vector to the k's component of the forcing function. All Caputo differential operators have the same initial point, 0. And as you can see from this notation here, the order may depend on k. That is the crucial point here in my talk. So we will introduce a shorthand notation. So we write this whole system of d individual scalar equations here in this vector form, where x is now the vector of solution components, f is the vector function on the right-hand side, and alpha up here is not a number, it's a vector as well, or a multi-index if you prefer. So this is something d-dimensional, and this shorthand notation is supposed to stand for just this up here. And then we have to distinguish two cases. Case 1 is the commensurate case, when all those alphas here, all the components of the vector alpha are the same. And the second one is the incommensurate case, and that's everything else. So for systems of this type, we want to investigate their stability. What do we mean by that? Well, let's introduce a simplifying additional assumption, namely that the right-hand side here of the differential equation satisfies f of t, 0 is equal to 0. And those zeros here are meant to be null vectors, and that's not scalars, but vectors. If that is the case, then we have a trivial solution, which is just the constant function that is 0 everywhere. And you can always get there by a suitable transformation. Our question is this system up here asymptotically stable? So that means if you pick out any solution, a completely arbitrary solution, this is of course just a differential equation system. We haven't specified any initial values, so we have multiple solutions. And if you pick out any of those solutions, does this solution tend to 0 as t tends to infinity? Or in other words, does it converge towards this trivial solution? And if that is the case for any solution, then we are saying this, this system is asymptotically stable. And that's a crucial point when you want to use such systems in the modeling of real-world processes. You don't want your process to explode. When we look at the commensurate case, this is something which is very well understood, and we don't really need to say very much about that anymore. Our question here is what happens in the incommensurate case. In the incommensurate case, what we know so far is relatively little and is relatively theoretical. So there are ways of reformulating this in equivalent ways, analytic ways or algebraic ways, by saying that certain zeros of certain functions reside in certain regions, but that is not very helpful in practice. So what we are looking for here is a constructive answer. We want to find out an algorithm which can answer this question here, this main question. Okay, so how do we construct this algorithm? Well, let's start by looking at the case of a linear differential equation system. And it's a very simple linear system. It's a system with constant coefficients for the moment. So our system looks like this here. The vector of fractional derivatives of the unknown solution is equal to some constant d by d matrix capital A times the unknown solution. That's the first special case that we're looking at. And we know very well what the stability properties of this system are in the classical case, in the integer order case. So that means when all differential operators have order 1. In that case, we know we have asymptotic stability if, well, if all eigenvalues lambda of the coefficient matrix A reside in the open left half of the complex plane. Or in other words, if for all eigenvalues, the real part is negative. So this is expressed here in terms of the Cartesian coordinates of the eigenvalues. In fact, for generalizing this, it is a bit more convenient to express this in terms of polar coordinates, which then reads that the argument of each eigenvalue is bigger than pi over 2. So that's the classical case, the integer order case, first order system. The first step towards generalizing this then means we introduce a commensurate fractional order system. So instead of having the vector where all entries are 1, we multiply that by some constant alpha 1. So now each equation has the order alpha 1. That's a commensurate system. And in that case, this criterion for asymptotic stability, which we have here in terms of the argument of the eigenvalues of the matrix A immediately generalizes. We now have to demand that the argument is bigger than not pi over 2, but alpha 1 times pi over 2. So that's a very straightforward generalization, and it's well known. It's been discussed for almost 30 years now. Okay, so let's just write that down once again. The system, the linear system with constant coefficients is asymptotically stable in the commensurate case if the argument of each eigenvalue is bigger than, and this should read the absolute value of the argument, I'm sorry, is bigger than alpha 1 times pi over 2. And there are multiple ways of expressing this differently, and that is convenient for our generalization that we are now looking for. So first of all, you can say this is equivalent to saying all zeros of the characteristic polynomial of the matrix are located in this region of the complex plane, have an argument whose absolute value is bigger than alpha 1 times pi over 2. Well, that's clear because the zeros of the characteristic polynomial are coinciding with the eigenvalues. And the characteristic polynomial is the determinant of this diagonal matrix, which has the variable lambda in each entry of the diagonal minus the coefficient matrix A. And then you can introduce a little substitution of variables. You introduce a new variable, lambda tilde, which is lambda to the power of 1 over the order of the differential equation, 1 over alpha 1. And then you can express this thing here in terms of the argument of lambda tilde, and you get rid of the alpha 1 up here. So that means the argument of lambda tilde is bigger than pi over 2, the absolute value of the argument, for all zeros of the characteristic function chi, which is, well, which you can generate from this characteristic polynomial by means of this substitution. So instead of lambda, we write lambda tilde to the power of alpha 1. So that's yet another equivalent formulation for the commensurate case. And this is the formulation that we can exploit to generate a corresponding result for the incommensurate case. And that is now in the incommensurate case, where the first equation has order alpha 1 and the second equation has order alpha 2 and so on, we just have to replace those exponents here. We have to, the first exponent is alpha 1, the second one is alpha 2, the third one is alpha 3, and so on. So we have to, we obtain this modified characteristic function. We have to find its zeros. And if the argument, the absolute value of the argument for each of them is bigger than pi over 2, we can prove that this system is asymptotically stable. And that's not only an if, it is an if and only if. And this is the very theoretic formulation that I talked about a couple of minutes ago. So this is the formulation which is equivalent analytically. You can prove that. But it doesn't really help you because, well, you need to find out the zeros of this characteristic function. And that's a really nasty task because it's, roughly speaking, it's a generalized polynomial with non-integer exponents. And you have to analyze that in the complex plane. So that is very, very challenging, and it's by no means trivial to find out where its zeros are. Okay, but we are talking about zeros of this function, and this function here is, if you look at the definition, is the determinant of a certain matrix. So we are looking at the case when the determinant of this matrix is 0. And that is something for which linear algebra provides yet another equivalent characterization. The determinant of some matrix T of lambda is equal to 0 if and only if this matrix is singular, or in other words, if and only if the system T of lambda times V, vector V, is equal to 0, has a non-trivial solution. That's plain and simple linear algebra, and in our case, the matrix, the matrix T of lambda, or a matrix pencil, as it's called in linear algebra, is just this difference diagonal matrix minus capital A. So the function here is just our characteristic function. And so we are looking at lambdas, values of lambda, for which this equation system, which is a linear equation system, has a non-trivial solution. And this problem is known in linear algebra as a nonlinear eigenvalue problem. Even though we have a linear equation system here, it's called a nonlinear eigenvalue problem because this function capital T is a nonlinear function of lambda. That's where this nomenclature comes from. Okay, so when you ask the folks in numerical linear algebra, how do you solve this nonlinear eigenvalue problem, then they tell you, oh, we have lots of algorithms for all sorts of different nonlinear eigenvalue problems, but not for this one. We don't have a readily available solution for that. What you can say, of course, and that's a simple exercise in complex analysis, the problem has finitely many eigenvalues, but it's not evident how many eigenvalues it has. So this adds another level of complexity. Okay, so to handle this additional level of complexity, let's introduce one more limiting assumption. And this limiting assumption is an assumption on the orders of our differential equation. So what we are saying is, or what we're demanding is that there exists some alpha tilde between 0 and 1, 0 is excluded, 1 is included, such that each alpha k, each order, can be written as this number alpha tilde times such a fraction here, where the numerator and the denominator are positive integers and they are co-prime. And we also demand that the largest of these fractions is equal to 1 and the smallest one is less than 1. So that means, this inequality here only imposes the restriction that we really have an incommensurate system. Otherwise, if this were not valid, it would be a commensurate system, and we already know how to deal with those. That's not interesting. So what effectively that means is that alpha tilde is the maximum of our orders. So that's something which is easy to achieve. And the other bit is that all the quotients alpha k times divided by alpha j must be rational. So not the so this is fulfilled if all the alphas themselves are rational. That's a sufficient criterion. It's not necessary. Now you may say that's a severe limitation, and the pure mathematician in me would agree with that. But on the other hand, we are talking about algorithms. We are talking about things that we want to implement on a computer. And there we are talking about finite precision arithmetic, and irrational numbers don't exist in finite precision arithmetic. So in some sense, it's a relatively natural restriction. Okay, so how does our algorithm work? Here's once again the definition or the connection between the given orders and the new numbers alpha tilde, rk, and sk. And then we look at all our denominators. the sk and find out their lowest common multiple, call it sigma, and then we define new numbers qk, which is rk times sigma divided by sk. When you look at this here, well, you know that sigma is a multiple of each sk, so sigma divided by sk is an integer, rk is an integer, so qk is also an integer. And those are values which can easily be computed from the given data, from the alpha case. Then we define some matrices. Matrix A0 is just the negative of our coefficient matrix. So that's also easy to compute from the given data. And for k running from 1 to dimension d, we introduce those matrices A sub k, which is just the k's coordinate unit vector multiplied by its transpose. So this is also a d by d matrix, a very simple one. It has a 1 in row k and column k, and it has zeros everywhere else. So all these matrices are very easy to compute, and in addition, at least the A1 up to AD over here are very sparse. They contain just one single non-zero element. Then we introduce one more substitution. We introduce a new variable for our characteristic function called mu, which is lambda to the power of alpha tilde divided by sigma. Remember, we've just computed alpha tilde and sigma, so this is also not a problem. And the result then is that our nonlinear eigenvalue problem is something which we can reformulate as a polynomial eigenvalue problem. So it has the same structure, some function of the potential eigenvalue times v, some matrix valued function is equal to 0. We're looking for non-trivial solutions v, non-trivial vectors v, which satisfy this equation system. And now our p of mu is this one here. So we have some constant coefficients, matrix coefficients, and mu to the power of qk. And as I just explained, all those qk's are integers. So this is a polynomial, a classical polynomial with integer exponents. And then our given nonlinear problem is something that we can reformulate. We want to find all the eigenvalues of this polynomial eigenvalue problem. Good. How do we do that in practice? Here's once again our polynomial eigenvalue problem. And it has we can collect some of the properties of this polynomial. So first of all, we can see that the degree of the polynomial is sigma. It's the lowest common multiple of the denominators of our fractions. Sorry, it's the least common multiple. Yeah, the smallest common denominator. You can also see that the leading coefficient is one of those ak. And all those functions do, and none of these matrices has full rank. So the leading coefficient is a rank deficient matrix. It does not have full rank. From the theory of nonlinear eigenvalue problems, you know that the number of eigenvalues that this problem has is sigma times d. The degree of the polynomial sigma multiplied by the dimension of each matrix d. Also, this problem has some eigenvalues at infinity. This is a peculiarity of nonlinear eigenvalue problems, in particular of polynomial eigenvalue problems, which naturally comes in if the leading coefficient doesn't have full rank. But those are eigenvalues which come in an artificial way from the construction of this problem. They are not zeros of our characteristic function, and so they are irrelevant for us. We can also find out how many finite eigenvalues it has. To this end, you have to add up all the qk's. And because each of the qk's is less than sigma, less than or equal to sigma, and only one of them, or is equal, that is smaller than sigma times d. So this number capital N, the number of finite eigenvalues, is always smaller than the total number of eigenvalues. And each of the required zeros of the characteristic function corresponds to one of those eigenvalues. And the multiplicities are the same. And by corresponding, I mean for each zero of the characteristic function that we have, which has a certain multiplicity, we can find an eigenvalue of this polynomial eigenvalue problem with the same multiplicity. This is not an equivalence. So there are more eigenvalues than the characteristic function has zeros. This eigenvalue problem has also additional eigenvalues which have nothing to do with the zeros of the characteristic function. And this might at first seem disturbing because we're interested in the zeros of the characteristic function. So if we manage to compute the eigenvalues, well, then we get them, but we also get lots of other numbers. And how do we distinguish those? I'll explain that in a minute. It's not very difficult. Okay, but before we do that, let's look at the numerical approach. A numerical approach is based on the concept of so-called companion forms or companion matrices. So we start from our given polynomial eigenvalue problem up here with those coefficient matrices. And based on those coefficient matrices, which are easy to compute and well known, we can compute another matrix, or rather two other matrices, X and Y. As an intermediate result, we compute a matrix B0, which is just A0. So no problem in computing that. That is the negative of our original coefficient matrix. It's a D by D matrix and it's dense, typically dense. The matrix Bj for j from 1 to sigma is, well, you can compute that by summing up some of the AKs. So this is also something which can be achieved very easily, gives you also a D by D matrix, and it's sparse. It's a diagonal matrix, effectively, which may have zeros on the diagonal. If you add up all those Bj's, you get the identity matrix, the unit matrix. And none of those Bj's has full rank. And then you construct those matrices X and Y. Those are block matrices. So the matrix X has B sigma here in the top left corner, and it has the sigma minus 1 times d-dimensional identity matrix in the bottom right. And everywhere else it has zeros. So this is something which you can compute very easily. And you can also see the dimension. It's sigma d times sigma d. And you can also see, because, well, here's a diagonal matrix, which is very sparse. B sigma is very sparse. Lots of zeros here. So this is a very sparse matrix. And then we have the matrix Y, the second one here, which has the other B matrices here with negative signs in the first block, in the first block row. And also lots of identity matrices and null matrices everywhere else. So this is also easy to compute. It has the same size as X, and it's also very sparse. So what does our algorithm look like? It's a classical trick in numerical linear algebra. So instead of solving this polynomial eigenvalue problem in d dimensions with a polynomial of degree sigma, we look at a generalized eigenvalue problem with those matrices X and Y. This is a linear eigenvalue, a generalized linear eigenvalue problem. So polynomial of degree 1. But dimension sigma times d. So we have to compute those matrices X and Y, and we have to solve this generalized linear eigenvalue problem, which is a standard task in numerical linear algebra for which algorithms are readily available. What can we say about this generalized linear eigenvalue problem? Well, first of all, the size is sigma times d by sigma times d. D is the dimension of our original system, which is typically small or moderate, but sigma depends on the orders of the differential equation system. It's the least common multiple of those denominators of the orders effectively, and that can be a pretty large number. So it could be that we're talking about a relatively high dimensional system here. You can easily see if you look at the definition of X, X does not have a full rank. It's rank deficient, so the problem also has eigenvalues at infinity. And in fact, the eigenvalues of this generalized linear eigenvalue problem are exactly the same as those of our polynomial eigenvalue problem that we had before. And what we know is we don't need to compute all of them. We only need to compute the finite eigenvalues. Capital N was the number of finite eigenvalues. We know how big that is because we know how big those QK are. And when you do that, you can look in, for example, in the MATLAB documentation, there's an algorithm available which is explicitly designed for this purpose. That's the Eichs function, not Eich, but Eichs. And that is based on the Krylov-Schur algorithm. So you call that function, and that gives you all the eigenvalues that you want. And you can explicitly tell the function how many eigenvalues you want it to compute. Okay, so you ask this function to compute all the finite eigenvalues. You know how many there are, and that's fine. Good. So now how does that work in practice? Well, it gives us lots of eigenvalues. And I said a few minutes ago, not all of them are relevant. So we have to distinguish the relevant ones from the irrelevant ones. First of all, the infinite ones are irrelevant. And by the particular way in which we compute or which we design the algorithm or call the function, those will actually not even be computed, which saves us a bit of computation time. There may be an eigenvalue at 0. If that is the case, if and only if that is the case, the coefficient matrix A of the given system is singular. So this is something that you can check in advance before you even start any other work. You can look whether your matrix is singular. And if it is, if such eigenvalues exist, then the system is not asymptotically stable. So you don't need to go into any further investigations. Then there's eigenvalues which are finite, but not 0, and for which the argument, the absolute value of the argument, is bigger than pi times alpha tilde over sigma. Remember, we have already computed alpha tilde and sigma, so we can check this condition. And then it turns out that these eigenvalues come into the consideration because of the substitution of variables that we introduced a few steps earlier. So those eigenvalues do not belong to zeros of the characteristic function. They are eigenvalues of the nonlinear eigenvalue problem, but they are not zeros. They do not correspond to zeros of the characteristic function. And that means we can discard them. And then there's the rest. Those where the argument, the absolute value of the argument, is less than or equal to pi times alpha tilde over sigma. And those are the eigenvalues that really belong to the zeros of the characteristic function. Those are the eigenvalues that we need to look at. And then the crucial question was, are the zeros in the open left half or in the closed right half of the complex plane? And this is something that we can also reformulate in terms of the argument of those eigenvalues mu. The first bit is when the argument, absolute value of the argument, is less than or equal to pi times alpha tilde divided by 2 times sigma. And this means we have an eigenvalue in the closed right half of the complex plane. And the others, where the argument is bigger than this number, but smaller than this, those are the eigenvalues in the open left half. And so in summary, that means our given system is asymptotically stable. If our eigenvalue computation algorithm returns only values in category 1, 3, and 4b. Otherwise, if we have an eigenvalue in category 2, an eigenvalue which is 0, no asymptotic stability. And if we have an eigenvalue here in 4a, no asymptotic stability. We have implemented the whole thing in MATLAB. The function head looks like this here. It returns three values. STBL is a Boolean variable, which is either true or false. It gives you true if the system is found to be asymptotically stable and false otherwise. CF zeros is an array of complex numbers which correspond to the zeros of the characteristic function. So that gives you more detailed information, not just that all zero or whether all zeros are in the left or in the right half of the complex plane or not, but also the exact location of those zeros of the characteristic function. And mu is also a complex array. It gives you a list of the finite eigenvalues, of all finite eigenvalues, including those that we can discard. We've tested it under a relatively recent MATLAB version and also on GNU Octave, and you can download it from the Zenodo repository. Here's an example, an 8x8 system with a relatively randomly chosen matrix, but the matrix has some eigenvalues with positive real parts. So the first order differential equation system with this coefficient matrix would be unstable. Here's our vector of orders of the differential equations. And you can see when you look at those numbers here, the smallest common multiple is 15. So sigma is 15. And that means the size of the generalized linear eigenvalue problem is 8 times 15. That's 120. So this matrix, as I said, has two eigenvalues in the right half of the complex plane. It gives you an unstable system for first order differential equation. But that doesn't necessarily mean anything about the fractional system. So we can compute those eigenvalues, and here they are. So this is a complex plane with one black dot for each eigenvalue. And we have those rays over here, the blue rays and the magenta rays. The blue rays designate the boundaries of the greater sector, so that's the boundaries of category 4. And the magenta rays, where the angle is just half of that for the blue rays, separate categories 4A and 4B. So what we have here is 120 eigenvalues in total. What we can also see is that 42 of those eigenvalues are at infinity, category 1. We discard them. We don't even compute them. We have no eigenvalues at 0, so there's nothing in category 2. We have 74 eigenvalues outside of the wedge limited by the blue rays. So that's category 3. That's those eigenvalues that just come in artificially, spuriously via our transformation of variables. So they don't really relate to any zeros of the characteristic function. In category 4a, that's where the eigenvalues which would indicate instability be located. That is between those two magenta lines, and you can see there's nothing. And finally, there's 4 eigenvalues between blue and magenta, 2 in the upper half, 2 in the lower half. Of course, this is symmetric. This picture is symmetric. It's always symmetric when the matrix is real. Symmetric relative to the to the horizontal, to the real axis. So in summary, we have no eigenvalues in category 2, no eigenvalues in category 4, and that means the system is asymptotically stable. Let's compute a solution numerically, pick some relatively randomly chosen eigenvalue, initial conditions, initial values here, and then we compute the solution, plot the 8 components. Here, this is the result. You can see we have a logarithmic scale on the horizontal axis, and you can see that each component, all those 8 curves, tend to 0. Good. So what can we see in this example? We can see that the number of eigenvalues that our algorithm needs to compute was 78. That's the number of finite eigenvalues. The size of the system is 120, so we have to compute much less than 120 eigenvalues, and that saves us a lot of computation time. And this is the situation that we have in practice very, very frequently. And we can also see that the fractional system with those orders is asymptotically stable, even though the system of first-order differential equations with the same coefficient matrix is unstable. What else can we do so? Now, well, we had so far required all quotients alpha j divided by alpha k to be rational. What do you do if that's not the case in your given problem? Well, you then replace the order vector alpha by a nearby order vector alpha star with rational, where this is the case, where you have rational quotients. And then you apply the algorithm to the system with the new order vector. And you can prove, although it's a bit tricky to explicitly formulate the conditions, but if the approximation alpha star for the given vector alpha is good enough, and that's very hard to precisely characterize what good enough means, then the stability properties of the original system are the same as those of the modified system. It is not always clear that a good enough approximation exists. In many cases, you can prove that this exists. It's not so easy to find it, but it's a task for future investigations. Let's take a look at one example here. So we have this 3×3 system where the orders are pi minus 2.5, Euler's number E minus 2, and the Euler-Mascheroni constant gamma. So we have something which rounded to 5 digits behind the decimal point looks like this. And what we can then do is we can approximate those 3 numbers here by something which has this rationality property. So for example, you can use those numbers here, which come in when you replace pi minus 2 by 7 over 8, pi minus 2.5 by 7 over 8 times E minus 2, and so on. And then you can improve and improve and improve the approximation and improve once again. And when you look at those components here, you can see, well, the middle one is always exact. The others get closer to the true value, and they get closer in a monotonic way. So when you go here down, numbers get bigger. It's monotonically increasing, and the same here. So each component in its own right converges towards the limit in a monotonically increasing way. What you know then in the commensurate case is when the order increases, the stability problems become worse. They deteriorate. The stability region becomes smaller. That's because of this alpha factor in the stability region. So when the order increases, stability properties become not so nice. And that means, so what can we say in the incommensurate case? At least what can we expect or hope for? When each individual order increases, the stability properties deteriorate. And that means the zeros of the characteristic function should move towards the boundary between stability region and instability region, or in other words, their arguments should get smaller. In our example, the characteristic function has 2 zeros for all our alpha values, and one of them is a complex conjugate of the other, and here is their argument. And you can see, indeed, this is a decreasing. This seems to decrease as expected. And then we can look at this problem from a symmetric perspective. So we now approach those orders from the other direction, from the other side. So we move there from the upper side. We get a decreasing approximation sequence. And well, the expectation is that as we move through that sequence, the arguments of the zeros become bigger. We are moving more and more into the stability region, and indeed, this is what we get. And one more example here, also a 3x3 system, same alpha. And now we look at a slightly different way of approximating this order vector. Still, it is monotonically increasing in each component. So what we would expect then from our previous example is the arguments of the zeros of the characteristic function should decrease. And in fact, when you look at this table, it doesn't exactly work. So from here to here, it's not decreasing, it's increasing. But then it starts to decrease. And if you would proceed further in that spirit, it would remain decreasing. So the message is that the monotonic behavior seems to set in when your approximation vector is sufficiently close to the exact one, but not earlier. And that's quite natural because, if the approximation is not sufficiently precise, then we don't even know whether the characteristic function has still the same number of zeros. That could also change because the number of zeros, of course, depends on that order vector alpha. What do we do in the case of nonlinear systems? Well, and if we have a nonlinear system, we have two main results. First of all, it's the inhomogeneous linear case. So we have to add here another forcing function. And then we can say if this forcing function tends to 0 and the homogeneous system is asymptotically stable, then the inhomogeneous system is also asymptotically stable. And if you also know that this tends to 0 with a certain algebraic decay rate, then the components of the solution also decay with a certain decay rate, namely the minimum of this decay rate of the forcing function and each individual order. And finally, the case where we really have a nonlinear problem, an autonomous one. And here we can say something in the case when this function f here is locally Lipschitz at the origin, and the Lipschitz condition tends to 0 as you concentrate on a region around the origin. In that case, you can also say if the linear system without this extra term is unstable, then this nonlinear problem is also unstable. On the other hand, when the linear system without the nonlinear bit is asymptotically stable, then the complete system is, as we say, Mittag-Leffler stable, which means we get this decay rate. So the solutions tend to 0, but not always. This works only when the initial values are sufficiently close to the origin. Good, so let me just conclude then with a couple of open questions. So in all my theory and my examples, the coefficient matrix here was constant. What happens when it's not constant? Can we find a complete theoretical characterization? I think that is possible. But how do you do that numerically? How do you constructively find the zeros of the characteristic function or whatever the appropriate generalized concept is? What exactly do you do when you don't have rational quotients? So how precisely do those zeros move as you approximate the order vector? How does the number of zeros change? And this is something which requires an approach based on totally different aspects from numerical linear algebra. I think it can be done, but it's a problem of a totally different nature. Good, yeah. So this has recently been published in Numerical Algorithms. It's already available online. It's not yet available in printed form, but you can look up everything, and I would like to thank you for your attention.
Thank you, Professor Diethelm, for the nice talk. For questions, please raise your hand. I'll call out your name in the order they appear on my screen. You can equally unmute your mic if you have a question. I doubt, Professor Diethelm, there are any questions today. Probably because we are approaching close to the summer. So if you have any, so if you have any final commentary or something, please please feel free to use this time. I guess none. Good. So possibly let's close this talk here today, and then we'll see you guys next week.
Thank you very much.
Thank you very much. Have a nice day.
Bye.